Welcome to Calculus. Today we will investigate graphing tangent and normal lines of polynomial functions, focusing on using rules that we have developed for differentiating polynomials to find equations of tangent and normal lines. We'll take a look at three examples. The first example here has 4 parts. So as we look at our function f of x equals x cubed plus 3x minus 1, we're really looking at 4 different tasks. The first thing I want to do is find the slope of the tangent line to the graph of each function at the indicated point. So we'll start with that first. To predict where we're going, we're also going to, in part B, find the equation of the tangent line. Part C, find the equation of the normal line. And then we'll check all that by graphing the function and both those lines on this plane. But again, let's focus on part A, which is finding the slope of the tangent line to the function f at the indicated point. One thing we need to recall is that a tangent line is a line that is intersecting the function at one point. And the point where we're considering our tangent lines will hit that function is here at 0, -1. So I do recall that the slope of a tangent line is really the way we define the derivative. So what we need to find first is the derivative of f of x. So I'm going to jump right in, find the derivative of f of x. So as I look at the terms, I got 3 different terms. And using that idea of sum rule and difference rule, I'm going to treat them one at a time. So using the simple power rule to differentiate x cubed, the coefficient 3 comes from the old power 3. X to the power of the old power 3 less 1. We'll simplify that in a moment. My second term there is plus 3x. So my derivative of that term is going to be applying the constant multiple rule, just a 3. And then the derivative of x, the linear parent function, is just 1. And my last term there in that f of x polynomial is -1. And I recall that the derivative of a constant is 0. So just to simplify that derivative, that is now equal to 3x squared plus 3. And what had taken us many minutes to derive using the definition of the derivative with these rules for taking the derivatives of polynomials, it becomes much faster. Now I am interested in the slope of the tangent line to the graph at this point, 0, -1. So the x value there is the 0, and that's what I want to evaluate this derivative at. So the derivative at 0 is going to be, let me write it as a separate line so that I don't get confused. So I'll even switch colors here. So the derivative at 0, let's put 0 in red, equals 3 times 0 squared plus 3. And when I go to evaluate that, 3 times 0 squared is just 0. That cancels, and this slope of the tangent line of the function f of x at the point 0, -1 is 3. We'll check that in a moment just to see how does that show up on our graph. Well, let's do that second part. So the second part is to find the equation of the tangent line. So there's 3 things that I need to plug into the point slope form. Y minus y1 equals m times parentheses x minus x1. And they are the slope I just found, which will be 3, x1 and y1, which come from the point that we're given up here. So I'm going to go ahead and label that x1, y1. So we won't hesitate. We'll just make our substitutions. So it's y minus -1 equals 3 times parentheses x minus 0. And that's a good equation for my tangent line at the point 0, -1. to be able to graph that, I do want to take it to slope-intercept form. So that becomes, if I simplify this equation, y minus -1 becomes y plus 1 equals 3x plus 0. And I can probably let the 0 go. I'm going to subtract 1 over. And I end up with this slope-intercept line, y equals 3x minus 1. So you can see if this is 3, the slope of the tangent line, I can check that that's still the case. The 3x, remember mx plus b, I see that slope is preserved. Part C is then asking us to find the equation of the normal line. So remember, for normal line, we use all the same information, but we find the negative reciprocal of the slope of the tangent. So that's pretty easy to find. The slope of the normal line is going to be take 3, flip it over, so 1/3, and then switch the sign so that it's negative. So that's the slope. So then to find the equation of the normal line at the point 0, -1, I'm going to again use the point slope form, y minus -1 equals the slope -1/3 times quantity x minus 0. I want to simplify that to mx plus b again. So that becomes y plus 1 equals -1/3 x plus 0. Similarly, I'll subtract 1, and this solves again very quickly. Y equals -1/3 x minus 1. The last part here is to graph the function along with those two lines here on the coordinate plane. So let's create a table for this function that we can use to help graph. Again, the function is x cubed plus 3x minus 1. And I'm going to go from -2 to +2 for my domain. And let's plot this function. So I need to calculate at -2. That's -2 cubed plus 3 times -2 minus 1. -2 cubed is -8. 3 times -2 is -6. So -8 minus 6 is -14 minus 1, -15. A little off my graph, but we'll keep going. -1 cubed plus 3 times -1 minus 1. -1 cubed is -1. Minus 3 is -4 minus 1, -5. 0. 0 cubed plus 3 times 0 minus 1. First two terms are destroyed by the 0 multiplier, so it's just the -1. That's the y-intercept. +1, 1 cubed plus 3 times 1, so that's 4, minus 1 is 3. And lastly, 2 cubed is 8, plus 3 times 2, 8 plus 6 is 14, minus 1 is 13. So let's graph. The first point I can really plot here is -1, -5. I can also plot 0, -1, 1, 3, and then the other 2 points on my table are out of range. So I'm just going to sketch this very narrow cubic function, and I'm going to label that f of x. So I do want to plot my tangent line and my normal line. So my tangent line is this blue y equals 3x minus 1. So that's going to have a y-intercept of -1, and then a rise of 3, a run of 1. And then I can reverse down 3, left 1, down 3, left 1. And that is my tangent line. So I'm going to go ahead and label that tangent. Y equals 3x minus 1. Last step here is to plot the normal line. So it also goes through that same point at -1, 0. I'm sorry, 0, -1. And then it rises fact, it falls 1 because it's negative, runs 3, fall 1, run 3. And I can reverse up 1, left 3, up 1, left 3. And that is my normal line. And that's the equation, y equals negative 1/3 x minus 1. And that completes this task. And definitely we can see that that normal line is perpendicular to the tangent at the point 0, negative 1. Let's take a look at a second example. So our second example has different questioning. So the questioning here has to do with horizontal tangent lines. So let's move that out of the way and give ourselves the 100% view. So in this case, we got 6 tasks. So the first one is to find the point at which the graph of the function has a horizontal tangent line. So what we'll start with, again, is just finding the derivative of f of x. And what we need to do is then interpret what does it mean to have a horizontal tangent line? What's the slope of a horizontal tangent line? But first, let's find the derivative. So the derivative of f of x, and here again, I'm going to apply those rules to speed up the differentiation. So constant multiple rule says the 3 stays put. Simple power rule brings down the power as a coefficient times the base to the old power less 1 minus the constant multiple rule has the 12 sit there. Derivative of the linear parent x is just 1, and then the derivative of a constant is 0. So that gives me the derivative here of f of x as 6x minus 12. Now, what we need to interpret the question is what are the points at which the graph of the function has a horizontal tangent line? So to find the slope of a horizontal tangent line, we just need to think, what's the slope of that flat line? Well, it's 0. So in order to find the x value where the original graph has a slope of 0, we set the derivative equal to 0 and then solve. So on this equation, I'm going to add 12 to both sides. And that gives me 6x equals 12. And then to find simply x, I divide by 6, and I see that the x value where this function has a horizontal tangent line is 2. So that's what I'm looking for in part A. I do need to find the y coordinate as well. So to do that, I'm going to take 2 and plug it into the original function. So not the derivative, but f of x. So I want to find f at 2. So again, I'm picking up the function. It's 3x squared, so 2 squared minus 12 times 2 plus 4. So 3 times 2 squared is 3 times 4 is 12. Minus 12 times 2 is 24. Plus 4. If I add and subtract those 3 values, 12 minus 24 plus 4, that's going to be negative 8. So y value is negative 8. So I could put those separately, or if I wanted to, I could bring them together as a coordinate pair, 2, negative 8. That is the point where the original function has a horizontal tangent line. Part B says, what's the equation for a horizontal tangent line? That's pretty immediate. Once I've got this point, remember the horizontal tangent line has a constant y value. So all I need to do is take that negative 8 and say the equation for that horizontal tangent line is y equals negative 8. That's just an interpretation of our point there from part A. Part C is asking us to write and solve an inequality to see where does the derivative have a value greater than 0. So I'm going to pick up the derivative that we calculated, 6x minus 12, and I'm going to set it up to be greater than 0. I'm also going to set up a second one for part D, where that derivative is less than 0. So we'll do both of those kind of side by side since they're similar tasks. So I'm going to add 12 to both. And for both, that puts 12 on the right side. So the part C here is 6x is greater than 12. Part D is 6x is less than 12. Notice it's a lot like the equation we solved in part A. Divide by 6 everywhere. And we see that for part C, we end up with the inequality x is greater than 2. So the derivative is a positive value when the x is greater than 2 on the original function. Similarly, the derivative has a negative value when x is less than 2 for the original function. Part D says to graph. So we'll create a coordinate table here and graph our points. So here I'm going to put part E on the far right. With a table. There's our x values, and what we'll calculate is the 3x squared minus 12x plus 4. So I'm going to take here 0. I see that this graph, it's a parabola that opens upward, and I can see that it's kind of shifted over to the right into quadrants 1 and 4. So I'm not going to start at -2. I'm going to start at 0, and I'll go out to 4. And that'll ensure that we get kind of a symmetric set of points in terms of our outputs. So I'll just plug in here. The 0 plug-in is real easy because 3 times 0 squared minus 12 times 0 plus 4 is just 4. Those first two terms are destroyed. So this goes through the y-axis at positive 4. 3 times 1 squared, so that's 3, minus 12 times 1, that's 3 minus 12 is -9, plus 4 is -5. Now 3 times 2 squared, that's 3 times 4, so that's 12, minus 12 times 2, so 12 minus 24 is -12, plus 4 is -8. If you recall, that's what we just calculated in part A. I believe that's the vertex. Let's see if this bumps back to -5. So 3 times 3 squared, so that's 3 times 9 is 27, minus 12 times 3, 27 minus 36 is -9, plus 4, and yes indeed, -5. So my prediction is that at 4, it has the y value of 4 to match the symmetry. 3 times 4 squared is 3 times 16, which is 3 times 16 is 48, minus 12 times 4, which is 48. So 48 minus 48, 0 plus 4 is 4. And that completes that pattern. So I'm ready to graph that function. So 0, 4, 1, -5, 2, -8. So it's definitely a dilated function. It's been stretched vertically. And then at 4, back up at positive 4. So our graph for our parabola, really it's got its vertex right at the lower edge of our coordinate plane here. There's f of x, I'll label it. And then the horizontal line that we had found in part B, y equals -8, is the horizontal line traveling through very lower edge of this coordinate plane. So that's the horizontal tangent line. And one thing we start to notice is, hey, that goes through the vertex. And we're going to make that connection as we go, that a lot of these critical points on functions have slopes of 0 for their tangent lines that pass through them. The last thing for us to do is part F. I need to describe the green graph in terms of part C and part D. So what does that mean? So in terms of part C and part D, what they're asking is where's the derivative greater than 0 or less than 0. So on part D, we're saying that on the graph, x is less than 2. If I were to highlight that, that's this left side. And what we could say is that what that means in terms of analysis of the function is that the slopes of the tangent lines for x is less than 2 on the original function are negative, because we started with where's the derivative less than 0 there in part D. And so you can think, okay, so what does part C mean? Well, part C was when x is greater than 2, so that's this right-hand side. And we started with that one talking about where's the derivative greater than 0. Well, remember, derivative is the slope of the tangent line. So in that case, slopes of tangent lines for x is greater than 2 are positive. And I think if we just sketched in a couple tangent lines, that one would be a negative slope and it would fall within the analysis here in part D. Similarly, if I put a tangent line on the right, that's a positive slope, and that would fall in with the analysis here in part C. So again, very useful to have these rules. It speeds up the process of finding the derivatives and making these analyses. It just makes it quicker. Let's take a look at a final example that really we don't have to do a whole lot for. So we got all these steps, but again, we just want to start with part A, which says find the points, if any, at which the graph of the function f has a horizontal tangent line. So what I'll do is I'll set up part A, but let's see what happens. So the derivative of f of x, this one's x plus e to the power of x. So we'll do it according to the sum rule. So by parts, derivative of the linear x is just 1. And derivative of the natural logarithm is, I'm sorry, the natural exponential is itself. So when I go to set this one equal to 0, 1 plus e to the x equals 0, and go to solve that, I'm going to subtract 1 from each side. And immediately I run into an algebraic dilemma. E to the power of x equals negative 1. And I'm forced to say question mark. When can I, or for what x value can I raise a base to that power and have it equal a negative number? This has no solution. There's no number I can put in for x in the power to have the output be negative. And so what we're forced to do really for this whole question is to say this whole function has no horizontal tangent lines. No horizontal tangent lines. And so when we look at the other parts, part B is not applicable. We could deal with part C, because really that's every value of x. Part C says when are the slopes of the tangent lines greater than 0? They always have to be greater than 0. Based on this fact, again, really I should include that equation right there. If I set that up, 1 plus e to the power of x is greater than 0 and subtract 1, that inequality where we're saying for what power of x, if I raised e to that power, would it be greater than -1? All x values. So again, it's another way of saying the slopes of the tangent lines for this function are always positive. We could graph this function. So if I were to just graph it, it starts on the negative side. Basically, the parent function for lines, that's the power of x one. And then as it hits the y-axis, it does attain sort of an exponential part. So that's the original function, x plus e to the power of x. But I don't have any horizontal lines to plot, tangent lines to plot there, because again, there's no minimum or maximum. That's really what we need in order to graph a horizontal tangent line. So a nice instance where we're saved by all positive tangent line slopes. We're grateful. So thank you for joining for this investigation of taking the derivative in order to find equations of tangent and normal lines. I'll let you find those tangent and normal line equations of your own. See you soon.